Question 8 asks us to find, or given an equation, and these are all parabolas, find the x-intercepts and the vertex. So we're asked to find values of x that create an output of 0, right? Y would be 0. And then the vertex is, if I can find the x-intercepts, the vertex is going to be midway between those two. That'll at least give me my x value. So let's go ahead and take a look at the first one here. In order for me to find the x-intercepts, right, the values, I need to find the values that will make this parabola equal 0. So what I'm going to do is I'm going to write this as this equation, 0 equals x squared plus 8x plus 15. And what I want to do is I want to rewrite it. Right now it's a quadratic and it's representing three different quantities, and I want to rewrite that as instead of the sum of pieces, I want to write it as the product of a length times a width. So in an area model, I'm going to write an x squared here and 15 here, and I can see when I multiply x squared times 15, I get 15x squared, and that's important because when I fill in these other two boxes, right, I need to get 15x squared in those also. Because if it is factorable, right, it has to be the case that the product of those diagonals are equal to each other. The other thing that I have to do is I have to break up this 8x. It has to be rewritten to fill in the other two boxes. So I'm looking for two things that have a product of 15x squared, and when I add them, they have to add up to 8x. And we've been here before. 3 times 5 is 15. So I know that it's going to be a 3x and a 5x. If I multiply those two, I definitely get 15x squared. So here's the 3x, here's the 5x. So you can see my diagonals are both equal. This is 15x squared, and this is also 15x squared. And I can see that the 3x and the 5x is exactly the same as the 8x in my original problem. So you can see everything's accounted for, right? In my original quadratic, I've got the x squared, I've got the 8x in the form of 3x and 5x, and I've got the 15. So if I go ahead and factor out the greatest common factor each direction, these would each be x, and 3 times x would give me 3x, and 5 times x would give me 5x, and you can see that 3 times 5 is exactly 15. So I can now rewrite this instead of as the sum of the pieces, I can write it as a product, right? A length times a width, so an x plus a 3 times an x plus a 5. And of course, the beauty of the product, and my motivation for doing this, is now I can use the zero product property to find the values of x that will produce an output of 0, right? So just by setting each one of these pieces equal to 0, I see that, oh, x is negative 3, that's one, and then the other x would be negative 5. So negative 3 and negative 5 make this, they make my original quadratic equal 0. Therefore, right, that's where I'm crossing the x-axis. Those are my x-intercepts. So I can say my x-intercepts happen negative 3, and at that point y is 0, and they also happen at negative 5, and at that point y is 0. So now let's see if we can figure out what our vertex is. So the vertex is the midpoint. It's between those two. So if I was to add the negative 3 and the negative 5, I get negative 8. And if I take half of negative 8, right, I have a value of negative 4. So I know that the x value for my vertex is going to be at the number negative 4. And so now the question is, how do I find out the value of y at that point? Well, I've got a machine up here that does exactly that, right? It says you give me an x and I'll tell you the y. So let's go ahead and plug that in, and I guess I'm going to use my calculator for this. So this is saying go ahead and take your x value and square it. So here's negative 4, And I'm going to very carefully square negative 4, right? Negative 4 times negative 4. And then I've got plus 8 times, and I'll go negative 4, so plus 8 times negative 4, and then finally plus the number 15. So when I plug in that x is negative 4, it's giving me that y is negative 1. So I now know that my vertex is happening at negative 4 comma negative 1. And I can also see that my x-intercepts are at negative 3 and negative 5. Now if I wanted to check that, right, I could look at the original quadratic function. So I'd hit the y equals, and I can enter x squared, and then again I would plus 8x, and then plus the number 15. So if I'm looking at the graph of that function and I hit trace, I believe when I press enter negative 3 for x, it should give me 0, and it does. It gives me 0 for y. And if I enter negative 5 for x, it should also give me 0, and it does. And the other thing that should happen is when I give it the number negative 4, it should tell me y is negative 1, and it does. So you can see I've got the correct x-intercepts and the correct vertex. So let's go on to, it says part B. Okay, there are 3 parts here. So part B, this is it's the difference of squares. So if I factor the difference of square patterns, this is going to be x equals, and it would be x plus 3 times x minus 3. So recognizing the difference of squares and being able to, factor that as the sum and difference of the square roots of those parts is very, very useful. And you can, verify this by looking at an area model of all things. So if I had an x and a plus 3, and if I had and I guess I'll put it over here, an x and a negative 3. If you look at it, this is x squared, this is 3x, this is negative 3x, and this is negative 9. So you can see, like in my original problem, right, there are no x's, and the reason why is because this negative 3x and this 3x cancel each other out, and we're left with just 0. So that's a beautiful thing about the difference of square pattern, is that the x values cancel like that. So I can see using the zero product property, if you wish, or by solving this by undoing things. But if I use the zero product property, I could see that x is negative 3 and x is positive 3. So those are the 2 values of x that will make this equation. Oh, actually, I jumped ahead of myself. If I set this equal to 0 because I'm trying to find my y-intercepts, right, those are the 2 values of x that will make the output of this function 0, which is what I'm looking for, because I'm looking for an x-intercepts. And when I'm crossing the x-axis, y is 0. There, I think I said it correctly finally. So let's go ahead and plug in our x-intercepts. We should be at negative 3, which makes y 0, and we should be at positive 3, which would also make y 0. And then finally, my vertex, let's see, the number that is exactly in between those two, right, in between, if I'm looking at the graph between negative 3 and positive 3, the value that's right in between those is 0. So x is 0 on my vertex. And if I plug 0 into that equation, it gives me the number negative 9. So that should hit all of those points correctly. And I'm just learning. So, and we're learning. So let's go ahead and look at it again anyways, even though I don't think we necessarily need to look at this one. So I'm just going to look at x squared and subtract 9. And as I look at this graph and then hit trace, again, things that should happen when I enter negative 3. Oops, I have to make sure I hit trace. When I hit negative 3, it should give me 0. It does. When I enter 3, it should give me 0. It does. And when I enter 0, it should give me negative 9, and it does. So it's definitely giving me those correct values. Okay, finally, part C. We are asked to find x-intercepts. That means that we're trying to find those places where this function's y value is 0. So I'm going to rewrite this function. I'm going to, as with this related quadratic equation, right? I'm looking for values of x that make y 0 when my function is x squared plus 3x minus 10. Again, having this in factored form would be easier to deal with because I could use the zero product property. So I'm going to go ahead and rewrite this sum of pieces as a length times a width. So I'm going to a generic area model, and I will write in an x squared and a negative 10. And I'm looking for two values of x that have a product of negative 10x squared. And when I add these things, it should add up to 3x. And I'm immediately thinking of 3 and 5. And I think I want to use positive 5x. I'm sorry, 3 and 5 and 2, and a negative 2x. There we go. Because if I multiply those, I do get negative 10x squared, and when I add them, I do get 3x. So I'll go ahead and rewrite this 3x, this middle term, I'll rewrite it as a 5x and a negative 2x. Perfect. So my dimensions again here are x. This would have to be a 5. This would have to be negative 2. So I'm looking at x plus 5 times x minus 2. And again, this product equals 0. So my zero product property tells me that my two values of x, and I'm taking a shortcut here, x is negative 5 and x is positive 2. So those are my x-intercepts. So at negative 5, this function equals 0, and at positive 2, this function equals 0. And then finally, my vertex. Let's see. If I add negative 5 and 2, and then divide by 2, I'm getting a negative 3 halves. So my x value at my vertex is negative 3 halves. The question is, what's my y value going to be at that point? So I guess I'll just go ahead and plug in the negative 3 halves up here. Let's see. Actually, you know what? I'm gonna use my calculator for this. Not that I'm a coward, but I am. Let's see. So I'm going to go ahead and grab the fraction template. So if I hit alpha and then y equals, you can see the first option there is this numerator denominator fraction template. And I'm going to enter a negative 3 over 2, and I'll just press enter. So there's that fraction. It's on my stack. I can use it quite nicely now. What I can do is I can say open parentheses, go grab that fraction, close parentheses, and then square it. That was easy. Plus 3 times, go up and grab that fraction, got it, and then finally minus the number 10. And when I do all of that, I get an answer of negative 49 fourths. Negative 49 fourths. So negative 49 over 4. So that is the value of, wow, that is the value of my vertex. That's y when x is at negative 3 halves. So let's go ahead and check this. I'm going to go ahead and hit y equals, whoops. I'm going to clear out my last equation. Oh, I don't need you. And I'll enter x squared and then plus 3x, whoops, not 3 squared, plus 3x, oh dear, x squared plus 3x, and then minus 10. There we go. Now I'll graph it and I'll hit trace. And when I enter negative 5, oops, I didn't hit trace. Now I'm hitting trace. When I enter negative 5, it should give me a value of 0, and it does. And when I enter 2, it should also give me a value of 0, and it does. And if I enter negative 3 divided by 2, negative 3 halves, it's giving me negative 12.25. Let me write that down, negative 12.25. My suspicion is that's exactly what this is, so let me quit and take a look at it. If I grab this fraction, oh, I can hit math and I can say turn that into a decimal. Doop. There it is. Yeah, so that's negative 12.25. It's exactly correct. So again, on this question, right? Um, for each graph, it says find the x-intercepts and the vertex. In order to find the x-intercepts, what we did was we rewrote the sum of parts as a length times a width, right? So the benefit of that is once we have the sum of the parts as a product of a length times a width, we have a product now, and we can use the zero product property because we're representing this quadratic as a length times width, right? If a times b equals 0, right, then either a or b is 0. So it's easy for us to find x-intercepts because those are values of x that make y equal 0. And then to find the y-intercepts, it's the one that's right in between those two. So we were looking at the in-betweens. And once I knew what x had to be, I was plugging that in to the original equation to figure out what y was.